So hello everyone and welcome back to another video. Today I'm going to code a Python package, which you can install using pip command from terminal. Using this package you can convert any video to ASCII just from a single command. And just from terminal. You can save it, in any format you like. So how will it work? Every video is composed by a set of frames that are played at a certain frame rate. Since a terminal has a specific number of rows and columns, we have to resize our video to adjust to the terminal size limitations. To reach a correct visualization of an entire frame we need to adjust the frame height to match the terminal rows, avoiding using more characters than the number of terminal columns. When picking a character to represent a pixel we need to measure the relevance of that pixel's color in the frame. Based on that we can then select the most appropriate character based on the relative luminance in colorimetric spaces, using a simplified version of the luminosity function. This function returns an integer in the range from 0 to 255. We assign a character according to density to show more colored surface for areas with more intense color, highest values. The reduced range of colors supported by the terminal is a problem we need to account for. Modern terminals support up to 256 colors, so we need to find the closest 8-bit color that matches the original pixel in 16 or 24-bit color. We call this set of 256 colors ASCII colors. Finally, when putting it all together, we will have an appropriate character for each pixel and a new color.
The code is a command line interface (CLI) module for playing videos in the terminal using colored characters as pixels or other useful outputs. It imports the player module, which contains the necessary functions for playing videos. The main function is defined, which sets up the command line arguments using the argparse module. It provides options for the input video file, the strategy to render the output file to export, and whether to play the audio track. The arguments are then parsed and stored in the args variable. Finally, the player.play function is called with the arguments provided, and the video is played according to the specified strategy and options. If a keyboard interrupt occurs, the user interrupts the program, it is caught and ignored. This code defines a function called play that is used to play or export a video from a file. The function takes in several optional parameters, including a file name, a strategy, an output file, an output format, and a flag to indicate whether to play the audio. Inside the function, a video engine object is created and the video is loaded from the specified file. If the play_audio flag is true, the code uses the FMPEG library to extract the audio from the video file and save it as a temporary WAV file. The video engine object is then set to include the audio. If a strategy is specified, the video engine's strategy is set accordingly. Finally, the video engine's play method is called to display the video using ASCII characters in the terminal. The optional output file and output format can be used to export the video to a file instead of displaying it in the terminal. This code is a module called video_engine.py that defines a class called video engine for video processing. The class encapsulates various video processing methods and stores variables throughout the process. The class has an initializer method _init_ that takes an optional argument called strategy. It initializes the render_strategy variable by accessing the strategies dictionary from the render_strategy module and assigning the corresponding strategy object based on the given argument. It also initializes the read_buffer variable to none and the with_audio variable to false. The class has a method called set_strategy that takes an argument called strategy and sets the render_strategy variable by accessing the strategies dictionary from the render_strategy module and assigning the corresponding strategy object based on the given argument. The class has a method called load_video_from_file that takes an argument called filename and loads a video file into the engine by using the cv2.videoCapture function. It sets the read_buffer variable to reference the loaded video. The class has a method called play that takes two optional arguments called output and output_format. It plays the video captured by using the specific render strategy set in the render_strategy variable. It calls the render method of the render strategy object and passes the read_buffer, the output_format, and the with_audio variables as arguments. This code defines a class called ASCII strategy that is used to process video frames and generate an ASCII output. The class inherits from a parent class called ASCII strategy. The main function in this class is apply_pixel_to_ASCII_strategy, which takes a pixel as input and applies a strategy to convert the pixel into a string of ASCII characters. The strategy used here is to convert the pixel into a grayscale ASCII character. The function calls another function called pixel_to_ASCII from the module image_processor, or image_processor_win if the platform is Windows. This function takes the pixel as input and returns a string representing the grayscale ASCII character. Overall, this class provides a way to process video frames and generate ASCII representations of those frames using grayscale ASCII characters. This code defines a class called ASCII color-filled strategy, which is a subclass of ASCII strategy. It contains a method called apply_pixel_to_ASCII_strategy, which takes a single video frame as input and processes it using a pixel parsing strategy. The pixel_to_ASCII function from the ePay module is called with the pixel and a density parameter of 2, which converts the pixel into a set of colored characters as a unique string. This method returns the resulting string. The code also imports modules called ASCII_strategy and image_processor, and checks if the platform is not Win32. If it is not, it imports a module called image_processor. If it is Win32, it imports a module called image_processor_win. The code is a module called ASCII_color_strategy.py that contains a class called ASCII Color Strategy. This class is used to process video frames and create an ASCII output. The module imports another module called ASCII_strategy and assigns it to the variable strategy. It also imports the sys module. If the platform is not Windows, the module imports another module called image_processor and assigns it to the variable ep. If the platform is Windows, it imports another module called image_processor_win and assigns it to the variable ep. The ASCII Color Strategy class is then defined. It is a subclass of the ASCII Strategy class. It has a method called apply_pixel_to_ASCII_strategy, which takes a pixel as an argument. The purpose of this method is to define a pixel parsing strategy to use colored characters. It uses the ep.pixel_to_ASCII function from the imported image_processor, or image_processor_win, module to convert the pixel into a set of colored characters represented as a string. The resulting string is then returned. This code is importing several libraries including time, sys, os, cv2, opencv, and tempfile. It then sets the value of the variable platform to 0 if the current platform is Win32, and 1 otherwise. Next, it imports a module called render_strategy using the dot notation. If the platform variable is 1, it imports a module called image_processor, otherwise it imports a module called image_processor_win. Finally, it imports the get_terminal_size function from the os module and assigns the values of the current terminal size to the variable default_terminal_size, which is a tuple consisting of the number of columns and lines in the terminal. This code defines a class called ASCII Strategy, which is a subclass of the Render Strategy class. The purpose of this class is to print each frame of an image in the terminal using ASCII characters. There is a method within this class called convert_frame_pixels_to_ASCII, which takes in a frame, representing an image, dimensions, representing the dimensions of the terminal, and a Boolean flag for new line characters. Inside the method, it calculates the number of columns and rows of the terminal, as well as the dimensions of the frame. It then determines the printing width based on the minimum of the number of columns and the width of the frame multiplied by 2, divided by 2. It also calculates the padding by subtracting the printing width multiplied by 2 from the number of columns. It then goes through a nested for loop to iterate over each pixel in the frame and applies a pixel to ASCII strategy to convert the pixel value to an ASCII character. It keeps adding these ASCII characters to a message variable. If the new line characters flag is true, it adds a new line character to the message after each row of ASCII characters. If the flag is false, it adds empty spaces to the message equal to the padding. Lastly, it adds a carriage return and new line character to the end of the message and returns the final message. This message represents the ASCII representation of the frame of the image. This code is part of a program or class that applies certain strategies to modify pixel values in messages. The first function, apply_pixel_to_ASCII_strategy, takes a pixel value as input and returns the corresponding ASCII representation of that pixel. It makes use of another function called pixel_to_ASCII from a module or class named DeepFake. The second function, apply_end_line_modifier, takes a message as input and returns the same message without making any modifications. This function does not modify the message in any way. Overall, this code seems to be a part of a larger program or class that applies different strategies to manipulate pixel values and messages, using functions from other modules or classes. This code defines a function called render that takes in several parameters, including a video capturing object cap, an optional output file name output, an optional output format output_format, and a Boolean flag with _audio. The function begins by retrieving the width, height, number of frames, and frame rate of the video using the cap object. If the frame rate is not available, it defaults to 30. If with _audio is set to true, the function imports the necessary libraries for audio processing, sets up a temporary file for audio data, opens the file and retrieves audio information, and creates a PyAudio stream for audio output. If an output file is provided, the function opens the file and writes initial lines depending on the output_format. Specifically, if it is set to sh, it writes commands to set up a shell script. The function then sets up variables for time calculations and counter, and clears the console or terminal screen. It enters a loop to read each frame of the video. Inside the loop, it reads the current frame, checks if there is audio data to be played, and sleeps if necessary to match the desired frame rate. If no output file is provided, it scales the frame according to the terminal dimensions, converts the frame pixels to colored strings, and writes the resulting string to the console or terminal. If an output file is provided and the output_format is set to sh, it scales the frame and converts the pixels to ASCII characters. Writes commands to the output file to display the frame in the shell script. If an output file is provided and the output_format is set to JSON, it scales the frame and converts the pixels to ASCII characters, writes the resulting lines to the array in the output file for each frame. After processing all frames, the function closes the audio stream and cleans up resources if with _audio is true, and clears the console or terminal screen again. Finally, if an output file is provided and the output_format is JSON, it writes the closing brackets to the output file to complete the JSON array structure. This code defines a function called build_progress that takes in two arguments, progress and total. The purpose of this function is to build a progress bar in the terminal. First, the function calculates the progress percentage by dividing the progress variable by the total variable and multiplying it by 100. This calculation is assigned to the progress_% variable. Next, the function calculates the adjusted size percentage by dividing 20 by 100 and multiplying it by the progress_% variable. This calculation is assigned to the adjusted_size_% variable. Then, the function creates a progress bar by concatenating a certain number of filled characters and empty characters. The number of filled characters is determined by the adjusted_size_% variable, and the number of empty characters is determined by subtracting the adjusted_size_% variable from 20. This string is assigned to the progress_bar variable. Finally, the function returns a formatted string that includes the progress bar, the progress percentage, and some additional text. The progress bar is enclosed in a set of vertical bars, and the progress percentage is converted to a string before being concatenated with the other elements of the string. The entire formatted string is indented with 2 spaces before being returned. This code defines a function that resizes a given frame according to a specified dimension. The function takes in a frame, presumably an image or a video frame, as an input and has an optional parameter for the desired dimensions. If no dimensions are provided, the default terminal size is used. The function first extracts the current height and width of the frame using the shape attribute of the frame object. The height is assigned to the variable height and the width is assigned to the variable width. Next, the function calculates the reduction factor which is needed to resize the frame. The reduction factor is determined by dividing the desired number of rows, from the dimensions parameter, by the height of the frame, and then multiplying by 100 to convert it to a percentage. The width of the resized frame is then calculated by multiplying the original width by the reduction factor and then dividing by 100. This is done to maintain the aspect ratio of the original frame. Similarly, the height of the resized frame is calculated by multiplying the original height by the reduction factor and then dividing by 100. The dimension of the resized frame is obtained by combining the calculated width and height in a tuple. Finally, the OpenCV function cv2.resize is used to resize the input frame according to the calculated dimension. The interpolation parameter is set to cv2.inter_linear, which specifies the type of interpolation to be used during resizing. The resized frame is then returned as the output of the function.